Okay, so let's get started. Today we will continue our discussion on virtualization that we started last time, and the focus of today's lecture is going to be on OS. Screen is off. You have the remote for the screen? This one? All right. Okay, so while the screen is turning on, what I was saying is we will continue our discussion on virtualization from last class, and today's class is going to focus on OS virtualization, which is the next layer up in the hardware software stack. So you use the OS interface and emulate it to sort of mimic some other interface. Okay, so we'll talk about OS virtualization. I'll talk a little bit about the internals, where you can use pair share schedulers to allocate resources either across virtual machines or across containers that are running on the same machine. We'll see how pair share allocation works. Okay? And then we will end with Docker and Linux containers, which you have already started using for the class. Okay? But before we do that, there are a couple slides that we couldn't cover last time when we were talking about para-virtualization. So I'm going to first cover them, and then we will switch to OS virtualization. Okay? So if you remember last time we were talking about type 1 hypervisors, and I said one way you can implement a type 1 hypervisor on a hardware that has no support for virtualization is to use para-virtualization. And in this case, because the hardware does not provide any support to implement a type 1 hypervisor, you have to run a modified operating system kernel where the OS has been modified such that all the sensitive instructions inside the kernel have been replaced with hypercalls. Okay? So when the OS needs to do anything sensitive, rather than executing an assembly instruction to perform that task, it is going to make a hypercall, which will then go to the hypervisor, and the hypervisor will make that will perform that task for the operating system. Okay, so that's the picture we had in mind. So the example of type 1 para-virtualized hypervisor is the Zen hypervisor. Okay, so the popular open source Linux hypervisor. It runs on top of any x86 processor, no need for any specialized hardware support. And what you will see it actually does is it has essentially it runs a modified version of Linux, which is essentially shown here as the guest OS. And then it has this notion of partitions or domains. Each VM actually runs inside its own domain. Okay, and there is a special domain called domain 0, which runs the control plane software. So all of the OS operations from the other domains or other VMs actually come to what's called DOM 0 or domain 0. And then the domain is actually talking to the Zen hypervisor, is a modified version of Linux here, which then actually runs on top of those. Okay, so it's an interesting way you can get around some of these hardware limitations that I was talking about. Okay, so that's all I'm going to say. I'll actually put that paper up. If you are interested, you should go read it. It's a very nicely written paper on how to implement virtualization and specifically para-virtualization. Okay? So before we move on to OS level virtualization, I want to talk a little bit about how you can virtualize other resources. Okay? Everything we talked about last time was virtualizing the processor or the CPU. Okay? And we had all these examples of sensitive instructions and privilege instructions and how you deal with them and so on. But if you think about a virtual machine, it is supposed to present abstraction of a full machine. Okay? All the hardware resources that are present on a physical machine have to be virtualized and exposed to the OS. Okay? So that includes disk, it includes memory, it includes a network interface card, all of those resources. Okay? So it's worth spending a few minutes talking about how other resources are handled, because we talked about just one so far, which is the processor. Okay, it's the main one, but you have to talk about or think about rather other resources as well. Okay? So how do you do memory virtualization? So the ideas are not very different from what we talked about previously. Okay, so remember that the picture I showed you was one where the hypervisor is running in kernel mode. Only the hypervisor has the ability to perform privileged operation, but the OS itself can try to allocate memory to applications and on, even though the OS does not have those privileges. Okay, so so in this case, the OS will continue to manage page tables because it thinks it's running on a real machine. Okay, it might create new page tables for a new process, for example, but that's a sensitive operation. Okay, so it cannot actually perform that operation. So it will trap to the hypervisor because it's trying to execute a sensitive instruction. Okay, the hypervisor then actually internally maintains a second page table, which is called a shadow page table. Okay, so that page table actually performs a mapping and is mapped to the page table that's visible inside the OS. So the OS thinks it performed the operation. Okay, so it's basically a shadow or a mirror of the page table inside the OS is maintained in the hypervisor. Whenever the hypervisor makes the change on behalf of the OS, that data structure actually becomes available to the OS, and it thinks that it allocated a new page table or it allocated more memory and so on and so forth. Okay, so essentially any changes to the page tables are also sensitive operations. So those are also not something that the OS can perform. So the hypervisor has to make those changes for on behalf of the OS. The way you do this is you actually make the OS page table read only. In the memory pages are marked as read only. So when the OS tries to update it, okay, it is going to cause a trap because that will be a page fault. Then that is going to get to the hypervisor. The hypervisor will then make that change. Okay, very similar to what we talked about last time, where anytime the OS tries to perform an operation, but it's running in user mode, it causes a trap, and then the hypervisor deals with it. Okay, same concept, okay, but for memory management. Okay, very quickly, I/O virtualization or disk virtualization. This one is a little bit simpler, okay, because what you have to do is create a virtual disk for the virtual machine. Okay, the way you create a virtual disk is on the native machine, you just make a very large file. Okay, just a standard file, but it's very large in size. Okay, and this file basically is then exposed to the virtual machine and the virtual machine actually exposes a disk abstraction using this file. Okay, whenever the OS tries to read and write to the disk, okay, what you do is you actually read or write to the file. So the file has the same size as the disk that is exposed inside the virtual machine, and to the OS, it just looks like it's reading or writing to a normal disk. But what the OS, not the OS, the hypervisor does is it is actually using a file to create a disk abstraction. So it's really not a real disk. It's a virtual disk or a logical disk, but the storage space is allocated using files, not using an actual disk in this case. Okay, so that's the basic idea. And if you created your VMs in Lablet 1, you will see that the VMs are actually files that are stored on your machine. They are very large in size, in that there may be several gigabytes in size. Okay, because that's basically the size of the disk that is available to the OS that's running inside the VM. Okay, so you are going to use files to create virtual disks in this case. Okay, now in case of VMware, those files are labeled VMDK files. So if you see any extension VMDK, those are actually VMware generated virtual disk files. Every hypervisor has its own format of how it is going to use those large files and expose them as disks to the OS. Okay, so that is I/O virtualization. Very quickly, I just want to give you some examples of where virtual machines were used. Some of this came up in questions during the class last time. Okay, so there are different use cases for virtual machines. An early use case was to create what was called a virtual appliance. A virtual appliance is simply a VM that has a pre-installed OS, pre-installed software. Okay, and then if you, rather than actually getting some software and installing it on your machine, you just download a VM, okay, which has already been pre-configured with the OS and software, and you just execute the VM, and then the software just starts running on your machine inside a VM, not natively. Okay, so this eliminates the need to configure complicated software on your machine because it's pre-configured inside the VM. Okay, this is called a virtual appliance. Okay, so it was one way by which software started getting distributed, because then you didn't need to download software, install it, configure it, and so on, which in case of larger pieces of software can be complicated. Okay? So you could use VMs and OSs in them to simplify that task. Okay? Now, virtual appliances are not as popular anymore, because what I just said is also can be done using containers and Docker. Okay? So Docker has now become the more preferred way to distribute software. So rather than creating an entire VM, you create a container, you install the software in it, you package it, and then you just hand it to someone. They can just deploy it, and you have some software running on the machine. No configuration is needed. Okay? So this was a use case, but it has been replaced with Docker containers, which are a lot more lightweight and more efficient to distribute. Okay. So where do you use it if not in virtual appliances today? This is technology that's heavily used in all data centers, right? So I mentioned that cloud computing platforms essentially run on virtualization. Okay? When a customer of the cloud goes and requests a virtual server, you're not getting a physical server. You're actually getting a virtual machine that's running on a physical server. The physical server may be much bigger. The cloud platform can construct multiple VMs, and each can be allocated to a different user. Each can run its own OS and have its own software running. And then the hardware is going to, the hypervisor rather, is going to multiplex these VMs onto the physical server. Okay? So cloud computing is a big use case. In the desktop computing world, this is used for software development, right? So if you want to do testing and so on, you can create an isolated environment inside VM, test your code, and if something goes wrong, you're not going to actually cause any issues on your native machine. It's isolated to that virtual machine. Okay? So desktop computing for software development, for testing, cloud computing to actually allocate resources to end users. In data centers, it's used for essentially running applications in isolated environments. Also, it's used for this use case, which is called server consolidation, which basically means that you can take workloads that are running on multiple machines, put them inside multiple physical machines, put them inside virtual machines, and then pack those virtual machines onto a smaller set of servers, making more efficient use of your hardware resource. Okay? So that is called server consolidation. Okay? Some of this we will come back to, but these are just some use cases I wanted to mention before we move on and talk about OS virtualization. Any questions from last time or anything I said today? We are going to switch gears and move from virtual machines to the world of OS virtualization and containers, which is a different virtualization technology. Okay, so let's talk now about OS virtualization. So if you recall the definition I gave for virtualization in general last time, I said it's a piece of software that uses the native interface to emulate another one. Okay, that was the definition of virtualization. Okay. In the OS virtualization, the native interface is the OS interface, is the system call interface. Okay. OS, when we say OS interface, we typically mean system call interface. Every operating system exposes a set of calls which are called system calls that applications can use to invoke OS services. Okay. So our native interface is a system call interface, and we are going to emulate a different one. It could be a system call interface of a different OS. It could be a system call interface of a different version of that same OS. Okay? Which interface you're emulating is not important, but you're using one to emulate another. Okay? So there are so this is basically what OS virtualization means. Now the interesting thing that you will see is basically it allows us, if you use OS virtualization, it allows us to isolate what are called user space instances, or isolate application processes that are running on the same machine. Okay? So it allows you to take a set of processes, put them inside an OS virtualization environment, which we will call containers. Okay? And then those processes can operate as a group. They're isolated from other processes that are running on the machine. Okay? So the outside processes that are outside can see all the resources, but you can restrict what processes inside a container can actually see. And so here's a picture to make that a little more clear. Okay? So So this is your hardware. Okay, the pictures are actually showing the same thing, but two different operating systems. So this is hardware, this is your machine. Okay, you just run a normal OS on top of this. Okay, that OS supports OS level virtualization, which is called containers. So these blue things are containers. Okay, so they will see that each of them is running some applications. Now, when an application runs inside a container, it sees a normal machine. Okay, like because it's virtualized, but it cannot see outside the container. It cannot see the other processes that are running. It's limited to seeing processes that are inside the container. Okay, so in that sense, you isolated it. You are basically limiting what it can see. You can also limit what type of disk resources it sees and so on. But the main thing you limit is what other processes are running. Okay? So that's a picture you want to keep in mind. Okay. Now, the thing that you will see that's different from what I showed you last time, okay, is that there is no hypervisor in this case. Okay. In hardware virtualization, I said you have to run a layer called the hypervisor, and then the OS is going to run on top of it. Okay. Here we did away with the hypervisor. We're just running standard operating system that have support for OS level virtualization. Okay, that's the first thing. And these containers are lightweight virtual machines. Okay. Why are they lightweight? Because if you look at the picture I showed you last time, inside each virtual machine, you run another operating system. You run a full-fledged OS inside each VM. Here, you don't do that. Okay. You're just running up normal processes. The OS that's running, the host OS, provides all OS level services to applications inside the container. Okay. In case of VM, there's an OS running on that VM that provides OS services. In this case, you did away with it. Okay. So you will see there is more efficiency here because there's no hypervisor, there's no second operating system. So there's much fewer software layers that you have to deal with. It just looks like a standard OS with applications running on it, except that the applications are put inside containers. Is this clear, what I said? Any questions on this? Okay. This is same picture, different OS. It's a OS no longer in existence called Solaris that came up with this idea very early on. You will see this hardware here. The green thing is the OS. So you will see some applications are running like normal. They run on the OS. Some are actually inside zones. Zones are the terminology for containers in this case. And then these applications that are running inside container are restricted in terms of what they can see, what they can do, and so on. Okay, so here's a picture to compare type 1 hypervisor, type 2 hypervisor, both of which we covered last class, and Linux containers. Okay, this is Linux, but pretty much all OS virtualization technologies very similar. Okay, so in this type 1 hypervisor, you have hardware, you boot a hypervisor. Okay, so that's the thing that's actually booting, and then you create virtual machines, more than one if you need. Inside each virtual machine, you run another OS. This is called the guest operating system, and then on that OS, the VM just looks like a normal machine, but it's actually not a real machine. It's a virtual machine. It's not a physical machine. Okay? And then you run apps and processes on that OS. Okay? And you can run different ones. All of them are running at the same time. You can run Windows here, you can run Linux here, you can run something else. It's not the same as dual boot, which was a question that somebody had asked last time. Okay? This is type 2 hypervisor, okay, which we also covered last time. You have hardware. Okay? On that hardware, you just first boot a standard OS, which we will call a host operating system. Okay? It just looks like whatever you have on your laptop or desktop. Okay? And then on that OS, you are going to run a special application, which in this case is an hypervisor. Okay? And that hypervisor provides virtual machine functionality. So then you can create one or more virtual machines. And then inside those virtual machines, like previously, you can run another OS. Okay? So you have guest operating system running inside the VM. You have the host operating system that's running on the hardware, and there's hypervisor as well. That's a type 2 hypervisor. Okay? And this is essentially OS virtualization. You will see that, again, you boot a standard OS, like the type 2 hypervisor, but there is no hypervisor in this case. The OS is all that you have. And then you construct these lightweight virtual machines, and then you run applications in them like the previous case. And the important thing is these lightweight virtual machines, which we are calling containers, don't have another OS running in them, like the previous case. It's just basically is using the OS that's already running on the machine for OS level services. Is that clear? The difference between the three things we have talked about so far. Okay. So as you can imagine, because there is less software layers in the case of OS virtualization, it is much more efficient. You can create and stop these containers very quickly, and like booting a VM, you have to start the VM, then you have to boot an OS, then the processes start running. Here there's no OS to boot up. You can, once the host OS is running, containers can be started very quickly, very efficiently. Okay? They give you bare metal like performance because there's little overhead here. Okay? Unlike the previous case where you have a second OS that you have to deal with. Okay? And it's lightweight. And so this has become a popular virtualization technology because it is much more lightweight, it's more efficient. It still gives you isolation guarantees like you had in the VM case, where these apps that are running in one container are restricted. They cannot see the apps that are running in another container. Okay? So these are all advantages of OS virtualization. Can anyone think of disadvantages over type 1 and type 2 hypervisor? Yes. Only the native OS can be used. You cannot use any other OS. That is correct. That is indeed a limitation. Here you can run other operating systems. Anything else? Okay, question you're asking, if the system calls from a container impact the OS. So inside this container, you can emulate, although you don't actually run a full-fledged OS, you can emulate the interface of another OS, right? So simple thing you can think of is you can, let's say, run Ubuntu as your host operating system. Let's say Ubuntu 24. Okay, but you want to run some software that only runs on a previous version of Ubuntu, Ubuntu 22. You can create a container that's Ubuntu 22 here. So you are using the 24 interface to emulate Ubuntu 22 interface. That's an example. Okay. Okay. So if you look at this picture, you'll see that there's another disadvantage, which is all containers rely on the same underlying OS. Okay. So what that means is if a container causes the OS to somehow crash because of a bug, all other containers on that machine will go down because you're sharing a common operating system. Okay. That's not the case in other hypervisor technologies because each virtual machine is running its own OS. So if this application causes this OS to crash, other VMs are not impacted, only that VM is impacted because that is a OS that's running inside the VM. Okay. So in terms of, this is the same kind of problem we had when we were talking about microkernels and so on, right? So you have a common OS, so all containers share it. So it's lightweight and it's a good thing in most cases, but from a pure isolation perspective, it's not as isolated because any problems in the OS below will impact all containers. Okay. All right. So now let's talk about a little more of the details of how you implement OS virtualization technologies. So essentially, what you need is and this is specific to Linux containers at the moment, which is called LXC, by the way. That just stands for Linux containers. Okay. So you need two types of functionality from the OS to implement containers, which is resource isolation and resource management. Okay. So what do these things mean? So let me introduce two terms here. So in the Linux world, containers are implemented using two types of functionality. One is called namespaces, another is called C groups or container groups. Okay. So what are namespaces and what are container groups? Okay. So namespaces provide a technique for process level, process-based rather, resource isolation. So you can isolate subsets of processes at a time, and I'll talk more about that on the next slide. And C groups allows you to limit how much resources processes can use. Okay. So one is doing resource isolation and one is doing resource management. Okay. So let me explain some of these details to you. Let's start with namespaces. So what is a namespace? Okay. The simplest way to understand namespace, I said it's process level isolation. The simplest way to understand this is namespace restrict what a container can see on the machine. Okay? Let's say you start a standard, forget containers for just a second. You start a standard application on your machine. Let's say you start a browser or you start a mail client. Okay? By default, that process can see every other process on the machine. Okay? It can see what other processes are running. It can actually also look at all the files on the machine. Any files that have the right permissions, of course, are visible to the process. Right? So by definition, we are not limiting what a standard process can see on an OS. Okay? Once you put that process inside a container, you can control what it can actually see. Okay? By default, once you put a process inside the container, all other processes on the machine become invisible to that process. Okay? You can no longer see the presence of other processes, even though they are there. Okay? So you essentially now you put that process in a container, so it cannot actually look outside the container and see what else is running on the machine. Okay? So you're limited it. Okay? You can also add restriction to see what folders or directories are visible. Okay? You can say this container cannot examine any of the files on the machine, or you can say only these volumes are actually visible inside the container. Okay? And then that's the only thing that processes inside can see. They cannot see anything else. Okay? This is done using this technique called namespaces. Okay? You can also so you can control what is called mounts, or which files are visible. You can control PIDs, process IDs, what processes are visible. You can actually see what network interfaces are visible. You can also control inside what users are visible. So which user accounts are visible from the outside. By default, inside a container, you can create new accounts, or you can say none of the accounts from the outside are visible, and so on. So you can essentially control what is visible inside the container. Is that clear? Okay. So that's namespaces. So then you can say, what does this C group do, or container groups do? Container groups or namespace is already restricted what you can see. Okay? Container groups, the way you want to understand this is how much resources the process can use. Not what you can see, but how much are you allowed to use. How much CPU are you allowed to use, how much memory is allocated to the process, and so on. Okay? So you can, for instance, start a container and say, let's say you have a 4-core laptop. Okay? You can start a container and say it can only run on 1 core out of the 4 cores. So inside the container, no matter how many processes you start or how much resources you want, you can only get 1 core worth of CPU cycles inside the container. So the other 3 cores are no longer available or even usable by processes inside the container. Okay? But other processes that are running on the machine, they can use all the resources because you didn't limit anything. Okay? So now you are limiting what the process can use. Okay? So you can set quotas on CPU usage. You can essentially allocate memory. You can say when this container starts, it should have 1 gig of RAM. Okay? So if the process inside tries to use more, then it will be denied. Okay? Even though you might have more RAM and it may be unused. Outside processes don't have that restriction. They can use all of the memory because the OS is not limited anything they can use. Okay? So this is essentially what you can do with C groups. Okay? So using namespaces and C groups, you can now restrict what processes inside containers can see, how much resources they can use, and provide this notion of isolation. Okay? That's basically the fundamental technology that containers provide. Okay? And when you have used your the Docker container that we gave you, okay, it's basically doing the same thing. Okay? So next time you go and start your class Docker container, okay, you can actually do type PS on the command prompt. PS just say list all processes. You will see that there are only 2 or 3 processes that will be shown, even though on the machine there may be more processes because those other processes are no longer visible. Okay? Same thing with files. Okay? The way we set up your class Docker is only files from the outside that are visible inside is your GitHub repository. Okay? That's mounted as your lab directory or a lablet directory. Okay? All other files are internal to the container that were just in the image. They are not the same as what are outside. Okay? So you could only expose some files inside the container, but then nothing else is visible inside the container. Okay? And so on and so forth. So I think there's something you can go try for yourself, and you can get a little more understanding of how this is done. Okay? So we will. So there are many this C groups, which is called container groups. There are many examples. Okay, so you can limit CPU, and you can use something called proportional shares. You can do hard limits, which say this container gets only one core, or you can do something called proportional share limits. And I'll talk a little bit more about that, which allow multiple containers to share the resources. You can do CPU sets, which is limited to cores. You can also try to limit how much I/O the container processes can do, so how much disk they can use. You can limit memory and so on. Okay? So I'll give you some examples of how this is done, but by and large, I think I'll skip this figure. I don't think it's even readable. I think it's too small. But what this is trying to show is that the way you implement Linux containers is at its core these two techniques, C groups and namespaces. And then you also implement a security model, which is an access control, which says what users IDs are available inside, and other security policies that say what network interfaces are visible and so on. Okay? So once you do this, you essentially have Linux containers. Okay? On other operating systems, okay, there are also container technologies. Okay? They by and large do the same thing, but there might be some differences. So I gave you basically what Linux containers do. They're the most popular container technology out there. Any questions here? Okay, question is container partitioning the resources. That's one way you want to think about it, right? So C groups are a way to partition resources. Okay, so it's not only are you partitioning resources, you have namespaces which also say that what resources can you see and what resources can you not see. Okay? Partitioning is just one part of the story. It just says I limit you to using so much memory and so much CPU. Namespaces say you cannot even, some things just become are no longer accessible to you. Some processes are not visible, some files are not visible, and so on. That's not partitioning. That's just restricting what you can actually access without part. But yes, it is a way to partition resources. Question is, can it run on native OS or virtualization? If you see this picture here, right, a container is essentially going to have namespaces and C groups. All containers are running on top of native operating system, right? And the container, the virtualization technology is the partitioning technology here. There's nothing else. Okay. Yes, question. Okay, question is, are C groups rules that allow you to say, well, first thing is namespaces tell you what is accessible or not C groups. C groups are more resource allocation, how much resources you can see. You think of them as policies, or one way to think of them are rules, but yes, that's how you basically say here's a set of policies that limit what a container can see. And that's what the OS will enforce. Okay, so question is, if you mount some files from the native machine and make them accessible to a container, is that using C groups or is that using namespaces? So in this case, it's using namespaces because you are essentially trying to limit which files are visible and which are not. So by mounting it, you're saying only those files are visible. Okay. If you want to then use C groups, you can say you will limit how much I/O you perform, which means I can limit the amount of writes you can perform, reads you can perform on the files that are visible. Okay, so namespace saying what files are visible, but it doesn't tell you what restrictions are put on how much I/O you can perform. That you can do using C groups. Okay, yes. The namespace and the content, same thing. There itself we are isolating. What is namespace? Question is namespace and container the same thing? Is that what you're asking? Okay. So namespaces and C groups are techniques that are used to implement containers. Okay. So when I said container provides isolation, these are the techniques the OS is going to use to implement containers. Right? Namespaces and C groups are how you implement containers, is the way you think about it. Right?
What is the level of that namespace is actually defining, because already a container is isolated in the machine.
Question is what is it that a namespace does, because a container is already doing isolation. So the isolation is namespaces. The way a container is performing isolation is using namespaces to implement the isolation. So it's not like there's something on top of it. Right? The way when I said containers performs isolation, the way you do it is using these two techniques. Okay, so the way you want to think about it, say if you say go implement a container technology, you will actually implement namespaces and C groups and use them, and that's contained. That's what containers mean. Okay. Any other questions? Yes. Okay, can you repeat your question? That you're asking between the difference between the type 2 hypervisor and containers, but what's the question? Okay, is the question is the difference between the two only the presence of the hypervisor? That's your question. Okay. The first thing is you have to understand virtual machines is a much more heavyweight virtualization technology. Okay? Virtual machines emulate a physical machine, a hardware of a physical machine. Okay? So it just looks like a PC, but it's all emulated in software. And then you have to boot an entire OS on top of the PC, which is the OS that's running inside the virtual machine, and then run application. So it just looks like whatever you do on your laptop, which you have an OS, you boot it up, you're an application. The same thing is happening inside a virtual machine. Okay? So in both type 2 hypervisor and container, there is a host operating system. Okay? And in case of type 2 hypervisor, the host operating system runs an actual hypervisor that provides a virtual machine abstraction. And in that virtual machine abstraction, you have to run another OS. So you will see in this case, there are same machines running 3 operating systems. Okay? The host operating system that you booted, and then 2 guest operating system, each of which is running inside the virtual machines, inside the 2 VMs. Okay? Now in containers, a much more lightweight model. There's only one OS that's running. Okay? There's no more OS running inside the container. Okay? Processes inside the container see the same OS that's already running in the machine. Okay? Processes inside a virtual machine do not see the host OS. They actually see the OS that's running inside the VM. Okay? It's important to understand these differences. But yes, in both cases, in type 2 and containers, there is a host OS that you start off with. Okay? But the virtualization technology is different, provide different abstractions. Yes. Okay, question. I'm not fully understanding your question. We are asking in type 2 hypervisor and container, who is providing the hardware? Oh, okay. So, so we are asking how is hardware, how are hardware resources allocated? So typically, it doesn't matter whether this answer applies to both type 1 and type 2 hypervisor. Hypervisors, whether they're type 1 or type 2, take some portion of the physical hardware on the machine, okay, and they allocate it to virtual machines. So when you create a VM, you have to say, I need to create a VM with 2 cores, and I need it to be given 2 gig of RAM, and so on. And then it's the hypervisor's responsibility at runtime to ensure that that VM gets that much resources. Okay? So the hardware resources, the actual hardware resources, are split across virtual machines running on that hardware, physical machine. Okay? This is true for both type 1 and type 2. Okay? Now in Linux containers, okay, it's the OS's job to allocate memory and CPU to a container. But that's no different from what it does for ordinary processes also. Okay? Even for a normal process, it's the OS's job to say you are going to get this much memory and then when you schedule it, you decide how much CPU you get. It's the same thing, except that containers allow you to limit it. Okay? So you enforce limits as opposed to other processes that operate without such limits. Is that clear? Okay. Question is, how is the container meeting our definition of virtualization where you present a different layer, right? Okay. So that's not actually seen in this picture, but what you have to realize is inside a container, okay, applications see some OS. Okay? Typically, if you don't do anything, they will see the same OS interface as the outside operating system. Okay? So the inside interface, the emulated interface and the native interfaces can be the same, okay? But they don't have to. Okay? Inside the container, you can have libraries, okay, that actually expose a different OS interface than what is inside here. Okay? That was the example I gave. Okay? Maybe you are running OS that is Ubuntu 24. Okay? So processes by default will see the Ubuntu 24 interface. Okay? But inside the container, you can say, I want Ubuntu 22 because I'm running some old application. They don't run on 24. They have not been ported. So these libraries that are in there will actually present a Ubuntu 22 interface, and then you will translate them to Ubuntu 24. That's an example where you emulated one OS interface with another OS interface.
So that library runs only for one.
Yes, each container has to have its own set of libraries that decide what interface you want to present to the OS. Okay? Or the other container might have some other interface. You don't have to say every container is getting Ubuntu 22 in the example I gave you. This one does not, might just see the native interface and so on. Okay, there's some question here. Yes.
Type 1 and type 2 hypervisor, how how there's a topic call and because the other container is also.
Okay, well, the question about what happens when there are blocking calls. If you have a process that is making a blocking call, what happens to other containers? That's your question, right? So the thing to keep in mind about containers is the way you deal with blocking calls are no different from how you deal with them for processes without any virtualization at all. Okay? So what does that mean? Let's say you take container one, this process running in there, process makes a blocking call or a system call or something like that. Okay, that system call is going to go directly to the OS, and the OS is going to start executing that system call. Okay, that process will block because it's waiting. Okay, but the scheduler is free to run other processes. Right, so other containers can continue to execute. That's the same thing that will happen without any containers at all. If process A does a blocking system call, it will wait. OS will execute it, and then but process B can continue to run. Okay, until that is done. So that's not going to change. There's no question. Question is there anything that is analogous to namespaces and C groups in type 1 and type 2? Is that your question? Yeah. So the way you implement type 1 and type 2 virtual machines is that you allocate resources directly to virtual machines, right? Just as C groups allow you to say this container gets so much CPU, RAM, and so on. When you create the virtual machine, you specify how much resources the hypervisor has to give it, right? And that's what will actually happen at runtime, right? And there is no question about namespaces because the OS here cannot see anything on other VMs because it's isolated. So you don't have to do anything more. The isolation is already preventing one OS from or one VM from seeing what is happening inside another VM. Okay. Yes.
Back to the difference. Looks like it's that the host operating system. Does that mean the hypervisor is just?
Okay. There's a question about in type 1 hypervisor, there is no OS. You boot the hypervisor, and the question is, does that mean the hypervisor directly deals with the hardware? Right? That's your question. Yeah. So as I had said, in Type 1 hypervisor, you boot the hypervisor. So the hypervisor is basically your OS. Okay, not a real OS in the general purpose OS. The way you want to think about it, the hypervisor is a special kernel which only provides virtualization functionality, as opposed to a general purpose OS kernel that provides standard functionality. So yes, to answer your question, hypervisor has to deal directly with the hardware just as a OS would, but it's only doing it for the purpose of dealing with virtual machine. You can't do anything else. Like you would run standard processes on other operating systems, you can't do that here. The only thing you can run are virtual machines. Okay? Yes. So you will only boot the hypervisor. That when you power on the machine, the hypervisor will boot up. It will just look like an OS, but the OS kernel rather, but it's a specific one that only provides virtualization functionality. All right. So let's move on and talk a little bit about proportional share scheduling, and then I'll say a little bit about Docker. But given that we now have a course Docker, some of the Docker stuff you probably know a little bit about already, but the proportional share is something that's worth thinking about a little more in a little more detail. So what is proportional share scheduling? Okay, so think about a scenario where you have either multiple VMs running on a machine or multiple containers running on a machine. Okay? I already said you can allocate specific amount of resources to either containers or VM, right? You can allocate certain amount of memory, certain amount of CPU share, and so on. Okay? How is that done? Okay? The way this is done is you actually have to implement some specific type of scheduling mechanisms either inside the hypervisor, okay, so that it can say this machine, this virtual machine gets 2 cores, that one gets 1 core. You have to enforce that using some scheduler inside the hypervisor here. Okay, just as your CPU scheduler, your schedulers for hypervisor, or in case of containers, you have to actually do that inside a standard OS as well. You can say how much resources are allocated using C groups that have to be enforced. So you have to have special types of schedulers to implement those types of allocation. Okay? So there are 2 ways you actually can do this. One is you enforce hard limits. Hard limit says that you say that this container gets 30% of the CPU or 20% of RAM. Okay? And then it's actually, so that's like a quota. Okay? You are just allocated it, no one else, no other container, no other process can use it, even if it's sitting idle, it's dedicated. Okay? So you basically created a partition and you said this container gets this much resources. So that's hard allocation. Okay? You can certainly do that, but there is a better way to do this, which is called fair share allocation. In a fair share allocation, you can still control how much is allocated to a container or a virtual machine. Same technique works in either case. But if a container or VM is not using its allocation, okay, you can reassign that to some other container. In hard limits, you don't. If you say I give this VM 30% of the CPU, even if you are not using that 30%, it cannot be reassigned. It's a hard allocation, it's static. Okay? Think of this as a more dynamic way to share resources. Okay? You specify limits, but if those allocations are unused, someone else can use them if they need it. Okay? So that's the way you want to think about it. The question is, how do you perform this type of allocation or scheduling? Okay, this is called proportional share scheduling, also called fair share scheduling. Okay? So that's the term you want to keep in mind. The idea is very simple. Okay? So the way you decide how to perform the allocation is you give a weight to you allocate or assign a weight to each container. Let's just forget VMs, the same thing. Let's just take containers for a second. Each container, when it starts up, it's allocated a weight. A weight is an integer. Okay? The weight actually determines how much resources are allocated to the container. Okay? Let's take 2 container example. Okay? There are 2 containers, A and B. Okay? You give each of them weight of 1. Okay? So basically, then the resources are allocated in the proportion 1:1. Okay? That means half the resources go to one container, the other half of the resources go to the other container. Okay? Now, if I have 3 containers and I give weight, each of them weights 1:1:1, okay, each of them will get a third. Okay? So weights, or if you did 1:2, if there are only 2 containers, you do 1:2. Okay? First one will get 1/3, the second one will get 2/3. So that's basically the ratio 1:2. Okay? So weights basically determine the ratio of or the relative share of the resource that is allocated to a container. Okay? So by controlling the weight, you can control what percentage of that resource you can allocate. And you can have a CPU weight, you can have a memory weight. They don't have to be the same. You can say you get one, your weight for CPU is 1, but memory is 2, and then you will get more RAM and so on. Okay? That's the one thing. The other thing which is more important here is the weight does not, okay, allow you to have a hard limit. Okay? Unlike the previous case, a weight, think of it as a soft limit. If the container is busy, it has processes that are running, you get the share that was allocated. So if you did 1:1, okay, and both containers have processes that are performing computation, each of them will get 50% of the CPU share. That's 1:1. Right? But let's say one container does not have much computation to perform. Even though you give it 50% of the share, it's only using 10%. So 40% is idle at this point. Okay? In proportional share scheduling, you can take that unused allocation and you can reassign it to other containers that might need it. Okay? So in this case, containers can get more than their share if they are unused and sitting idle. Okay? But if every container is busy, you get exactly your share. Is that clear? So this is a better way of sharing resources because you are not letting resources go to waste. In hard limits, if the resource that you have allocated is not used, it's going to be wasted. So you can't reassign. Okay? In this case, resources are not wasted because if there is any process or a container that's willing to use it, you can reassign it and have that container make progress. Okay? So this is basically the concept of proportional share scheduling. So the two things you want to keep in mind is the way you control how much resources are allocated is through this notion of a weight. Okay? A weight basically determines the fraction of the resource you are going to get. Okay? And the second thing is all allocations are essentially based on the weight, but if you do not use the fair share allocation that is allocated to a container, it can be reassigned. Okay? Those are two concepts, but now I'll show you an algorithm to do this. Yes, your question. Okay, question is who is assigning the weight? Whoever actually configured the container and started it essentially has to specify, okay, how much resources is to be given. If it's a hard limit, you say this container gets a core and it's dedicated core. Whether you use it or not, it cannot be given to anyone. Or you can say this container gets a weight of 1, that container gets a weight of 2. So whenever you start containers, there's basically a specification of how much resources to allocate. Okay? So the owner of the machine who's starting these containers can control how much resources are allocated to containers only. Okay. Yes. Question is it not automatic? Is it manual? It's not manual in the sense of every time you have to specify it. You have to have a configuration file that is just going to be read and used when you start the containers. Okay. Is that clear? Okay. So let me show you a simple algorithm to do this. Algorithm is called weighted fair queuing, WFQ. Okay. It's a widely used algorithm, although I am explaining it in the context of allocating resources to containers or virtual machines. This is used in many different contexts. It is used in networking. They're used in routers in the networking world to allocate bandwidth to different applications. So you can allocate weights, and then the application gets network bandwidth in proportion to its weight. Okay? So here's basically how it works. Okay? Let's say there are n applications. Each of them is given a weight, which is in this case an integer. Okay? Application I is given a weight of Wi. Okay? So one gets W1, and they're just integers. Okay? So I'm just giving you notation. So once you have n of these applications, each application gets Wi over the sum of all W's. Okay? So essentially, you take all the weights, you add them up. Okay? That's your denominator, and the numerator is your weight. Okay? So if you have 1:1, okay? Okay, so you'll basically you get half. Right? If you have 1:2, you get 1/3 because the denominator is just sum all the weights, the numerator is your weight. So that's your ratio of what you're going to get. Okay? That's your fair share. Okay? But here is how the algorithm actually works at runtime, because you may not be using your fair share. Okay? So what the algorithm has to do is it has to track how much CPU, in this case, you're just doing CPU allocation. So you have to track how much CPU service our container has received so far. Okay? And based on that, you have to essentially schedule containers based on their weights. So for example, if you have one container with weight of 1 and another container with weight of 2, okay, you have to basically give one time slice to the first container and then give 2 time slices to the second container. So you get 1:2 ratio. Okay? You cannot just do round robin and give equal time slices, then you are not enforcing 1:2. Okay? So the scheduler has to decide how many time slices to allocate to each process based on its weight. Now, okay? And this is how it is done. Okay? It essentially keeps track of a counter. Okay? Counter is how many time slices have been allocated to this process. Okay? Every time you allocate a new time slice, you are going to increment the counter by the length of the quantum divided by the weight. Okay? So essentially, this counter is simply tracking how much CPU service you have received so far, and it has to be in proportion to your weight. Okay? So as you can actually do the very simple example to do the math. I'm not going to do the whole thing, but I'll just give you 2 steps of this algorithm. Let's say 2 processes start, they get weights 1:2. Okay? And both have start with counter of 0, which means no has been allocated so far. Okay? So initially, both of them have counters value 0. Okay? The idea is at each time step, you pick the container with the lowest counter and schedule it. Okay? That's the container that has received the least relative CPU share. Okay? And you want all of them to get the fair share. So initially, both of them are 0. So you can pick either one. Let's say you pick the one with weight of 1. Okay? And let's say quantum length is also 1. Okay? So what is this counter going to get incremented? You start with 0. Okay? So it says SI is SI plus Q over WI. So that's 0. Q is 1. W is 1. So the counter value becomes 1 after it got 1 time slot. Okay? So now you have 2 applications. The first one counter value is 1. Second one is still 0. Okay? So you always pick the least one. So you'll pick the second one. Right? And then you execute it. This one has a weight of 2, because we said the weight is 1:2. So now after it runs for 1 time slot, what's the counter value? Okay. Q is 1, W is 2. Half. Right? So for the second application, after it ran for 1 time slice, counter value gets incremented from 0 to 0.5. Okay? So the first application has value 1, second is half. Okay? You always pick the least one. So you'll again pick the second one. Okay? You will run it again, and now the counter value will take to 1. Okay? And now both are equal again, and the same thing will repeat. So you gave the first application 1 time slot, second application got 2 time slots. That's proportion of 1:2. That's what you wanted. And then you will repeat this. And so long as they're running, it will all be fine. Okay? So essentially, after each quantum, you update the counter value to SI is Q over WI. And then you essentially take the min of this, and then that's the one you pick. Okay? And then the counter values also have to be, when you increment them, you also have to compare it with the min counter value of any process in the system and SI plus QI, and update it that way. The reason you have to do that is if some process goes to sleep, okay, it can't get scheduled, so its counter will not change. Okay? Other processes will start making progress, their counter values will get incremented. Okay? And then when this process wakes up, it will have the least counter value in the system, and then it can just hog the resource for a long period of time just because it went to sleep. So you don't want to penalize other processes because some processes are blocked. So whenever you wake up from getting blocked, your counter value has to jump to whatever is the min counter value of all active processes in the system. Okay? This prevents you from hogging resources. So that's why there is a max there. Okay? That's a detail that you have to only worry about if processes go to sleep and so on. Otherwise, this is the main thing. You are going to use that equation there to decide how much share you get of the CPU. Okay? This is called weighted fair queuing or proportional share scheduling. Okay? You essentially assign weights to processes, and this very simple technique ensures that the amount of CPU time you get is in proportion to the weight. Is this clear? Okay.
Besides the
Okay, the question is SI the resource share? SI is not the resource share. SI is a counter that you keep for each process that decides how much time have you CPU time has been allocated to the process so far from the beginning. It starts at 0 and keeps incrementing. Okay, so it's not the resource share. The resource share is the weight WI. Okay, the weight determines your resource share. SI is the amount of service you have gotten so far. The weight is the share that you should be getting. Right? Okay. So this, I'm not going to go into the details here. This is just showing you that this scheduler WFQ is implemented in many operating systems, including the Linux operating system actually uses this. So if you use this scheduler, you can allocate weights and ensure that containers get share in proportion to their weights and so on. Okay. So the last thing I want to talk about today is Docker. Okay. So we talked about what is OS virtualization. I gave you the basics. Okay. I showed you one scheduling algorithm that shows how can you allocate resources to containers and make sure that they get the resource shares are enforced and so on. That's done using schedulers that are running inside an OS or inside a hypervisor that enforce those limits using weights. Okay. Or there could be hard limits as well. Okay. The third thing we'll talk about is what is Docker and how is it related to everything we've been talking about, OS virtualization and so on. Okay. So the way you want to think about Docker is it is an Linux OS virtualization technology, okay, that gives you additional software tools to make containers easy to use. Okay. At its core, okay, Docker is essentially Linux container. So it will have namespaces, it will have C groups. All of that is hidden from an actual user, but that's what is there underneath. But it also gives you additional tools that allow you to package software inside a container, distribute that software, and so on. Okay. So it is essentially, Docker is essentially Linux containers, okay, plus some additional software engineering tools that makes containers easy to use. Okay. That is shown in this picture. Okay. This is the same picture I had shown you previously for Linux. The Linux container picture is actually here. That's already a picture I showed you. This green thing is what Docker has added. So it took Linux containers and added additional tools that allow you to make it easy to create containers, remove containers, distribute containers, and so on. Okay. So in a sense, it's just Linux containers with additional tools that make it very easy to use. Okay. That's the way you want to keep this notion of Docker in mind. So you have other, and by the way, Docker is not the only Linux containerization technologies. There are many of them. Okay. There's one called Virtuoso. There's one called vServers. There's another one called LXD that builds on top of LXC. And there's Docker. Docker is the most popular one. Okay. But all of these other ones, they're all open source. If you have a Linux machine, you can actually install them and use them just as you can use Docker. Okay. So Docker adds portable container deployment across machines. That's the tool, right? So you can create a container image. Okay. You can distribute that image. Someone else can download the image and run it, and then you essentially can create a container on that machine. So it allows you to distribute your software to other users. So it's portable in that you can construct it on one machine and send it to another machine. Okay. So it's application centric, which means that you are expected to essentially create Docker containers with applications in them and distribute them for use. Okay. That's what we did for the class. We created a class container that has all the applications you need to write code. Okay. So it's a development container, a dev environment. Okay. You can have, it also provides tools to build these containers easily. Okay. And you use this already. You have a build script that automatically built a container. Right, it installed, it was automated, it installed all the software, and the image was created. Okay? And it also allows reuse. Right? So if you update that build script, you will see that it can actually reuse what's already been done. Okay? So all of these tools make Docker a very easy containerization technology. It's widely used, okay? And you can use it for all kinds of use cases, software distribution, for doing development environments, creating development environments, using them to deploy services as well. So far, you only used Docker to actually write code, but you will see as we go along in this course, we'll also use Docker to deploy code. Okay? It's also used at runtime. You can actually deploy applications on cloud using Docker and so on. So the applications will run inside containers on cloud servers in that case. Okay, so it's not only used for development, but also for deployment. Okay. All right. So this is a picture I wanted to show you. Okay. So, but here's a question to ask. So Docker is basically a Linux container technology. Okay. But all of you who have maybe a Windows or a Mac, okay, are also using Docker. Okay. The question is, how is Docker running on a Mac or Windows if it's actually a Linux containerization technology? The question clear? What I'm asking? Okay, so one answer is it can use OS virtualization. You're saying it will use Mac or Windows interface to create Linux interface. You could do that, okay, but Docker is actually not using that because it actually runs on the way it's built is runs on Linux because it's LXC technology. Okay. If you did that, you have a true OS virtualization where you built a container, a Linux container using Windows or Mac. Okay. But that's not actually what is happening on your machine. Any other thoughts on why is it that you can run Linux containers on other machines? Yes. Okay. Okay. Question is, can you have Docker be a virtual machine inside a type 2 hypervisor? Okay. So in fact, if you do not use Linux to run Docker, you run any other platform, whether it's Windows or Mac, okay, your Docker containers are not actually running on directly on Windows or Mac. Okay. What Docker desktop does is it creates a hidden virtual machine. Okay. A type 2 is actually runs a type 2 hypervisor under the hoods. Okay. It actually has a small Linux kernel as a VM inside on that type 2 hypervisor. And then Docker is actually running on that Linux that it starts up. So when you start Docker on Windows or Mac, okay, it is actually creating a type 2 virtual machine on your machine and is running Docker on Linux on inside that VM. Okay. All of that, because they built it well, is all hidden from you. But there is actually Linux running on your machine when you start Docker if you are running on Windows or Mac. Docker is not directly running on native Windows or native Mac and using real OS virtualization. That's one way you could have done it, but that's not what they do. Okay. They have a tiny Linux kernel that starts up, and then you have OS virtualization on top of that Linux. So it's always running on Linux. Of course, if you have a native Linux laptop, Docker will run natively like you show here. There's no extra thing running. So in fact, what will actually happen if you have a Mac is going back a few slides. So this is the picture you will have. So you run Windows, okay? You start Docker. Okay? Behind the scene, you'll start a hypervisor. It will boot Linux inside the hypervisor. Then there will be Docker running there. And what you're seeing is that Docker and your Windows and Mac. All of the middle stuff is hidden from you. Okay?
In Docker, there is a hypervisor.
The question is, in Docker, is there a hypervisor? By default, there is no hypervisor. I'm just explaining how Docker will run on Mac or Windows, not natively on Linux, because it is always going to have to run on Linux. Yes, the question is there hypervisor code? Yes, there is hypervisor code. In fact, on Windows, you probably installed WSL, which gives you a hypervisor built into it. But same thing is true of Mac. Okay, yes, question. Okay, question is the code in the Docker desktop or do you need another hyper? So when you install Docker desktop on a non-Linux platform, it ships with a built-in hypervisor, okay, and built-in Linux kernel. Any other questions here? Yes. Yeah, question is if you see Linux containers, is the host or Linux? Yes, Linux containers only runs on Linux. Other operating systems have their own containers, but that's not to say other operating systems don't. We only covered Linux containers because the world of Docker, that's the most popular containerization technique. So when you're running Docker, you're always running on Linux. regardless of what you have on your machine. If you have a non-Linux machine, there's actually a hypervisor and Linux running behind the scenes. So Docker can only run on Linux. Okay. Any other questions here before we wrap up? Okay, so this is Alexia already mentioned this. Okay, very quickly, Docker images and use cases. So you already constructed a Docker image for the class. You built one, right? So you probably know what an image is. So image is basically the set of files that make the container. When you execute the image, you construct a container. Okay, so the image is basically the data, all the files, and so that's something that you have, and then you have to execute it. It starts a container, and then the process is executed using the files that are inside the image. Okay? Now, Docker uses some interesting file system techniques that allow you to not install files multiple times. They use something called union FS that only install the additional files that are not already present on the underlying OS. It has all kinds of optimizations like copy on write, which I will not talk about now. We'll come back to this later. That makes it very efficient to construct an image, to start an image, and so on. And their basic idea is you essentially, once you build the image, you should be able to deploy it anywhere. Right? So technically, the image you built on your machine, right, you should be able to copy it and give it to someone else, and they should be able to run that image. Okay? And that's why it's portable. Or alternatively, we could have constructed a 677 image and just given it to you. Then you would not have to run the build script. We just gave it to you so you can build it yourself, but that's not necessary. Okay? We can construct it and we can just distribute it as part of the Docker hub. You can download it from there and run it. Normally, you do not build your Docker containers, okay, images. You just deploy. They're already distributed on the Docker hub. You just download them and run them. Okay? But in this case, because you're learning about these technologies, we had you build your own images as well. So you can actually push and pull from the repository and just run it. You don't really have to build these things. Okay? So one last thing, and then we'll end here. This is the very final case study in virtualization. Then we'll move on to other topics. This is a case study called Planet Lab. Okay? Planet Lab is essentially a test bed for students to do research experiments. Okay? Essentially, you should think of it as a distributed cluster across universities, where each university has a small set of machines, and then they say, let's use this to do research experiments. And then you take all these machines across all these universities and make a distributed cluster, okay, where the machines are all spread out. So as a student, you can go and say, I need maybe 3 machines to do some experiment. Maybe I'm deploying some web service and I want to do some testing. And then you can get some resources on machine on University A, some other machines on University B, a third set of machines on University C. And then you can essentially log into those machines and run experiment. Okay? That was the idea behind Planet Lab. So they built this large test bed where each university contributed some machines, but then you could, as researchers or students, use machines at other universities. Okay? Now, why am I saying all this? So what I wanted to actually say is the way they built all of this is using containerization technology. They didn't use Docker, but they used a very similar technology called vServer. That's another Linux containerization technology that did effectively the same thing. Okay? So if you wanted to run some code on some machine at another university, they would actually construct a container for you and create a user inside the container, and then you can log into the container and run your code. Okay? So that was called a slice. Okay? So you get a slice of each server. That slice is effectively a container. They're constructed and they use C groups to limit how much resources you can use. Okay? So the interesting use case of using containers to build a distributed cluster. Okay? And this is a one that is built specifically by students and faculty members to do networking and distributed systems research. Okay? The name has changed. This is the old testbed. The testbed still lives under a different name, but this is how they made use of this containerization technology. Okay? So that's a use case to keep in mind. That's all I want to say about virtualization today. We will continue next time with some other topics.